Hi, I'm Doug Baldwin. This video supplements the free online text Introduction to Theory of Computation by Maheswari and Smid by contributing to a proof that's missing from that text. In particular, the text suggests without proof that every pushdown automaton accepts a context-free language. This video and an accompanying prose document, Pushdown Automata corresponds to context-free grammars, also by me, provide the missing proof. The proof consists of a method for constructing a context-free grammar from any pushdown automaton, and a formal argument that the resulting grammar generates the same language as the automaton accepts. This video helps you see how the construction works by exploring an example. To follow that example, you should be familiar with context-free grammars and with Maheswari and Smid's definition of pushdown automata. You should also have read the preliminary discussion and construction parts of my proof, although not necessarily the correctness part. The example uses a pushdown automaton that accepts strings consisting of one or more A's followed by an equal number of B's. The key strategy for accepting such strings is to count A's from the first part of the string on the automaton's stack and then match them against B's from the second part. For each A in the input, the automaton's start state thus adds a star symbol to the stack as a counter, regardless of what was there before, and moves on to the next input symbol. When the start state sees a B in the input, the automaton removes a star from the stack and enters a second state. In this second state, the automaton moves over B's from the input as long as they match stars on the stack. If this matching process reaches the end of the input and the $sign at the bottom of the stack simultaneously, the automaton removes the $sign, thus emptying the stack and stopping. As I start building the grammar, notice that if I follow the construction verbatim, I'll get an immense number of grammar rules. Fortunately, it's usually possible to dramatically reduce the number of rules because the verbatim construction captures every computation that any automaton with a given state set, tape alphabet, and stack alphabet might potentially do, while any specific automaton will only do a small fraction of those potential computations. One strategy for reducing the number of rules is to first eliminate variables that correspond to obviously impossible configurations of the automaton, and then follow the construction steps for writing grammar rules, but using only the remaining variables. In the case of this example automaton, notice that it can't possibly have non-empty lookahead in state Q0, and can only have empty or blank lookahead in state Q1. So right away, any variables whose subscripts involve state 0 with any lookahead at all, or state 1 with symbols A or B as lookahead, corresponds to an obviously impossible configuration of the automaton. As a result, the only variables I need to consider when building the grammar rules are those whose state and lookahead subscripts are 0 epsilon, 1 epsilon, or 1 blank. Now that I've ruled out a lot of impossible variables, I'll list the remaining ones and see what I have. To make this list, I find it easiest to metaphorically treat the subscripts as numbers with 3 digits, where the first digit is a state and lookahead combination, the second digit is a stack symbol, and the third digit is another state and lookahead combination. Then I just count through all such numbers buildable from digits I've identified as possible for the automaton in question. Using this idea on the example, my first variable is v sub 0 epsilon star 0 epsilon. Then come v sub 0 epsilon star 1 blank and v sub 0 epsilon star 1 epsilon, and suddenly I've used all the possible third digit values. So now I advance the middle digit to $sign and step through the state and lookahead combinations in the third digit again. Eventually I get 6 variables whose subscripts begin with 0 epsilon, and am ready to continue to subscripts that begin with 1 blank and 1 epsilon. Here, however, I can use transition patterns from the automaton to eliminate a few more impossible variables. In particular, if you look at the automaton, you'll see that once it reaches state Q1, there are no transitions that can take it back to state Q0. Since the first state in a subscript is the state the automaton begins a computation in, and the second is the state it ends that computation in, this transition pattern means that any subscript whose first state is 1 and whose second state is 0 corresponds to an impossible computation. Eliminating variables with such subscripts while finishing the list gives me 8 more possible variables. Now I can move on to writing grammar rules, knowing that the variables I've listed, plus of course the start variable, are the only ones I need to worry about. To write the grammar rules, just match each transition in the automaton to one of the rule-generating instructions of the construction, and then apply that instruction to the specific states and symbols of that transition. For example, the transition from state Q0 to itself on tape symbol A and stack symbol $, matches the first instruction in the construction because that transition replaces the top stack symbol and advances the tape. Substituting specific states and symbols involved in this transition for the generic ones from the construction, I'll get rules of the form v sub 0 epsilon $XX rewrites to A, followed by v sub 0 epsilon $YY, followed by v sub YY $XX, where XX and YY range over all possible state and look-ahead combinations. Intuitively, these rules say that the automaton can clear a $sign from the stack while going from state Q0 with no look-ahead to some other state and look-ahead combination XX by reading an A, which removes the first $sign but replaces it with a star and another $sign and leaves the automaton in Q0 with no look-ahead, then reading a substring that clears the star while taking the automaton to intermediate state and look-ahead combination YY, and finally reading another substring that takes the automaton from that intermediate state and look-ahead combination to the ultimate one while clearing the $sign. I can find the XX and YY combinations by just searching my list of variables for ones whose subscripts match the partial subscripts in the emerging set of rules. For instance, v sub 0 epsilon $XX matches v sub 0 epsilon $0 epsilon, in effect saying that XX can stand for 0 epsilon. So I can extend my partial rules to include some of the form v sub 0 epsilon $0 epsilon rewrites to A, followed by v sub 0 epsilon star YY, followed by v sub YY $0 epsilon. Then searching for variables that can match v sub 0 epsilon star YY and v sub YY $0 epsilon, I find v sub 0 epsilon star 0 epsilon and v sub 0 epsilon $0 epsilon, i.e. YY can stand for 0 epsilon. Thus, one complete rule is v sub 0 epsilon $0 epsilon rewrites to A, followed by v sub 0 epsilon star 0 epsilon, followed by v sub 0 epsilon $0 epsilon. Building more rules in this manner from all the other possible XX and YY values eventually gives me 7 rules for this first transition. The other transition from Q0 to itself on tape symbol A and stack symbol star also corresponds to instruction 1, and I handle it exactly as I did the first transition, producing 7 more rules. The transitions on tape symbol B and stack symbol star, namely from Q0 to Q1 and from Q1 to itself, both correspond to instruction 3 of the construction because they advance the tape without replacing the top stack symbol. Applying this instruction to those 2 transitions adds 2 more rules to the grammar. The last transition, from Q1 to itself on tape symbol blank and stack symbol $, corresponds to instruction 4 of the construction because it does not advance the tape or replace the top stack symbol. Thus, this transition adds 2 more rules to the grammar. Finally, instruction 5 in the construction gives me rules for rewriting the grammar's start variable. Of the 4 rules this part could produce, 3 of them involve possible variables, and so I add those 3 rules to the grammar and am done. This is the end of this example of how to construct a context-free grammar from a pushdown automaton. The example progressed from an automaton through a reduced set of possible variables to the complete rules of the grammar. You can firm up your intuition for the construction by trying to use the grammar I built to generate some strings you know the automaton accepts, for instance AABB. Whatever you do, have fun with pushdown automata and context-free grammars, and thank you for watching.